Welcome to my talk about events for reactive and AI-powered frontends. My name is Dev Agrawal. Yes, my name is actually Dev. It's not an abbreviation. I work at Smart Data as a software engineer, and I make YouTube videos about full stack development and architecture. So if you like my talk today, make sure you check out some of my YouTube content and connect with me on Blue Sky. I am on Twitter as well, but these days I kind of prefer Blue Sky. So I don't actually need to tell you all that event-driven architectures are amazing. You all already know that, which is why you're here at EDA Summit today. But I still want to highlight the things that we like the most about this way of building systems. We like that our systems are asynchronous, so they can work independently and not block each other. We like that our systems are loosely coupled, so we can build and break them independently. And we like that our systems are eventually consistent, so they better represent the real world. The more we lean into events, the more we benefit from these nice properties. Now let's see how we have evolved these architectures over time to better take advantage of asynchrony. We start with what I call the zeroth generation, which actually doesn't take advantage of async at all, really. Here, everything is synchronous pulls. The red arrows here show request-response cycles. Everything is temporally coupled. You all know why this is bad, right? I don't need to dive into too much detail. Then we take one step towards async by introducing queues. We can push messages into queues, which is shown here using a green arrow. Then our services can pull from these queues and do some work. This doesn't completely eliminate all our synchronous operations, but we now have a way to decouple and unblock certain workflows. Finally, we get to where I'd assume most of us either are or are trying to get to, which is a fully push-based asynchronous architecture. Now, this is a very high-level timeline, so obviously there's a lot of steps in between these generations, but I'm presenting an oversimplified view of this evolution that only looks at a single dimension, which is how these services interact with each other. So in the second generation, we have replaced our queues with event stores that themselves push into other services and trigger reactions, which might then again push into something else. We are also taking advantage of event sourcing for its time traveling benefits and CQRS for its nicely separated reads and writes. But what about our frontends? We revolutionized how our backend systems work, but how do our frontends know what's going on? Well, if you're unlucky, you're likely doing classic REST APIs, which are typically just CRUD operations exposed over HTTP. This likely means that any business workflows are getting duplicated on the client side by stitching together these CRUD operations. And you're likely overfetching data because your endpoints are very generic and not use case specific at all. This also complicates state management on the client side because once again, you're just using generic CRUD operations and attempting to keep the client state in sync with the server state manually. Rest assured, this is not a great place to be. Generic REST APIs are the easiest to build, but the most difficult to consume and to build on top of. Maybe you realized that REST API conventions are dangerous and decided to just build ad hoc remote procedures as you need them. So you are building a feature on your front end, you realize you need access to some data or run a workflow, you quickly whip up some logic and throw it in an endpoint, invoke it from your front end, and call it a day. Not having to deal with conventions makes your APIs single purpose. But you might also be tempted just to take an existing endpoint and add some more logic to it, make it configurable, and have it serve multiple features. This might lead to overloaded procedures that have way too much logic in them. This also doesn't really save you from complex state management on the client because you still need to keep the state in sync with the server somehow. Oh boy. I will say this, if you are using GraphQL already, you probably are not struggling with the same problems as everyone else. GraphQL is the pinnacle of APIs, and the tooling around it is insane. But at the same time, it is so tough to get right, both on the client and the server. I would love to recommend GraphQL as the de facto choice for everyone, but unfortunately, it's just too much work for most projects. Then we get to something that we are a lot more familiar with. CQRS fits very nicely into our event-driven architecture and offers a really nice revalidation model that almost completely eliminates all our complex state management problems. You run a command, and you simply revalidate the queries to get updated data. No need to manually try to keep the client state in sync. It has a lot more structure than ad hoc RPCs, and it doesn't have the same technical overhead of GraphQL. And it feels like a natural extension of our event-sourced system, because queries are just projection of event streams. They can be built, disposed, rebuilt as we please. So most of the time, this is where we want to be. Here's the problem, though. As we evolved our backend systems over time, the client-server communication stayed more or less the same. Our clients still have to make synchronous requests to the services and receive data or trigger commands. So when I put everything like this, the next step in the evolution feels obvious. We can eliminate the last bit of synchrony that we have in our architecture and start pushing updates all the way to the edges of our system, which in this case is our front ends. But how exactly do we do that? Let's step back a little and look at how you might be doing CQRS today. Here we have our client side under the line and the server over the line. We have a log of events on our server that push into our projections. And when the clients need some data, they make a request to the server that runs a query. The query goes over the projection and returns the result. When the user does something, the client sends a request to invoke a command. The command pushes an event at the end of the log and returns a status or result to the client. Pretty straightforward. In this model, our frontends get to be just dumb UI layers on top of our commands and queries. All the work happens in synchronous request response cycles. We don't need complicated state management because, like I mentioned earlier, the clients can just run a command, and when it completes, revalidate all the queries that are currently active, so the user always sees up-to-date data. But this also means that the interaction latency is really high, because every interaction will cause at least 2 requests to the server in a sequence. You invoke a command, wait for it to resolve, then refetch your queries, wait for the updated data. So we trade off latency for simplicity. If you don't want all the active queries to revalidate because it's wasteful and you have too many queries on the page, you can specify which queries should get revalidated after a command. So you get a bit of efficiency back for a little more manual work. We can make this model better by making the queries into real-time subscriptions. Now, instead of synchronously requesting data whenever it's needed, the client simply opens up something like a WebSocket connection and subscribes to a query. Whenever there's a new event, the projection gets updated, the query will rerun, and send the updated data to the client, which can update its UI. Commands look pretty much the same, not much you can do there. Now our front ends are real time. Our queries are recomputed live as new events come through, and updated data is always pushed to the client instead of the client having to pull it. This reduces interaction latencies by a lot, because as soon as a command pushes a new event into the log, the subscriptions can almost immediately start recomputing. So clients don't have to wait to hear back and then make another request to query data. We also don't have to manually specify which queries should get revalidated on the client after a command, because real-time projections will ensure only the queries that are actually affected by this new change get recomputed and pushed to the client. Okay, now this is a bit more complicated, so bear with me. This is what I call event sync. The core idea is that we are now pushing the event log itself from the server to the client. You can see that the client-server boundary has moved all the way up here. This means that projections can be built directly on the client side now. We can take our event log and build up whatever projections we need for whatever feature. They can be as small or as large as needed. There's a bit more going on on the command side. You can see that we actually have commands on both the client and the server. We first invoke the command on the client, which will push an event into our client log. This is just an emulation of the actual command, which will run on the server. The server command will then push the event into the server event log, which will then be pushed into our client. That was probably a lot, wasn't it? But I want to argue that it's very worth it. Our frontends are now much smarter. Remember, our commands and queries are a part of our business logic, and now they live on the client side. We get incrementally updated projections. We don't have our queries rerunning over the entire projection every time it updates, and then serialize the entire result data to the client, which then has to deserialize the data and compare to the existing UI to figure out what has changed. Instead, we simply push events as they happen, which mutate our in-memory projections on the client, and our UI can respond to the precise changes that were made by the event. This is a lot more efficient than any other model that we have looked at for querying data. On the command side, we push an event into the client log first. This is called an optimistic update. We are emulating the state that we hope we will get to when the command succeeds. This completely eliminates any interaction latency. Every interaction updates the UI immediately, instantly. And if for some reason the actual command fails on the server, we roll back the optimistic update, and the UI reverts back to its previous state. We can show an error message to the user if we want as well. Now, it might be a little jarring for the user to do something, see the UI update, but after a second or two, see their update disappear. So the user experience in the error cases gets a little worse, but the user experience in the success cases gets much, much better because there is zero latency between the interaction and the UI update. As a bonus, we can implement highly collaborative features like Google Docs or Figma by using CRDTs, or conflict-free replicated data types. I'm not going to dive into too much details of what CRDTs are, but essentially, if we want a multiplayer collaborative experience for your users where they don't lose updates, a CRDT is very, very helpful. But it also needs some infrastructure in place for optimistic and real-time updates like we have here. Let's take a quick detour and talk about LLMs. Generative AI is the new hotness, and you likely want to explore and experiment with LLM functionalities for your users. You probably also want to ensure that your LLM features are nicely wrapped in some nice looking UI on your front end. Right now, you might be doing something like a simple request response call to your LLM. Now, along with all the other disadvantages of synchronous calls, which I'm sure you already are familiar with, this has another big downside. LLMs are really slow and they take a long time to formulate a complete response. Thankfully, we have HTTP streaming, so they can stream responses as they are formulated, but having an HTTP request open from the client for so long has its own downsides. This is especially true if you're using serverless compute. You don't want to have a Lambda function open for so long, especially when all it's doing is proxying data from your LLM to the client. But you probably know that, so you're already on your way turning those LLM responses into events that your services can react to asynchronously. Now, if you have this capability to sync events from the server to the client, your LLM responses can automatically make their way to the clients as well. You can add as many of these workflows as you want, and as long as they communicate in events, you don't have to do anything extra to integrate LLM features into your front end. You can see the power of decoupling through events and how it enables rapid expansion of features. Let's walk through a couple small examples to explore what this could look like. Imagine we have a submission gallery app for a hackathon. You can go to the gallery, scroll through projects, click on one of them, and it opens the project details page. To show this page, we are going to use the project submitted event and the project reviewed events. We can build our simple projection on the client side for this specific page that gives us all the details of the project and a list of all the reviews it has received so far. Let's say that we want to add an AI summary. All we have to do is initiate a workflow whenever there's a submitted or a reviewed event, because the summary can be based off not just the project details or documentation, but also the reviews it has received. The workflow will resolve in a project summarized event with the AI generated summary, which will then be synced to the client. All we have to do in our projection is to take the latest project summarized event and render a little box on the side with that summary. All the plumbing for how the data goes back and forth the network is already done for us. We simply needed to write some event handlers and update our UI components. Let's look at another example. Say that we want some sort of semantic search for the projects. All we would need to do is trigger a workflow to generate an embedding whenever a project is submitted. We can take the resulting embedding and create a projection or create a project embedding generated event. That was a lot of words. We can then take these events and create a projection for embeddings, and our semantic search can simply use this projection. This feels very straightforward, but the really nice part is that we can do this entire thing on the server or on the client or hybrid. So our project embeddings projection can live on the client-side database like SQLite or even in memory if the dataset is small enough. We can also generate the embeddings on the client itself if we have LLMs that are running locally on the user's device. And because the events are automatically synced, any part of this workflow can be moved from the server to the client or back to the server as we want. There's a sample implementation of this gallery app on my GitHub if you want to see what event sync looks like in practice. Now, I know as soon as I said that we are going to sync the event log from the server to the client, some of you had red alert going off in your head. Are you crazy? You're exposing all the sensitive domain events and their structures to the client? That sounds so bad. Well, if you don't like exposing your internal event schema or data, you can simply come up with a different format that you are okay with publishing to the client and add a simple transformation step in between. We already do this with regular data because we don't want to expose our database schema to the client. This is basically the same thing. There's a catch though. When you have different event definitions for the server and the client, the optimistic updates get a bit more complicated. When it was the same events on both sides, you could simply create the same event on the client as you would do on the server. But now you need two different methods for your commands, one for the client log and one for the event log. I still think it's worth the effort just because the instant UI updates feel so nice. And when I use applications these days that make me wait for every single interaction, I just get annoyed. I just want my apps to feel fast so I can do my work. Obviously, none of this comes without trade-offs. Every step of the way, we are making our front ends a bit more complex. We are adding more and more work on the client-side app, making it smarter, giving it more business logic. And at the end of the spectrum, we have something called the local first app. Local first is kind of an overloaded term, so I'm not going to go in depth too much. But the core idea is that the copy of the data on the client is the authoritative source of truth, not the copy that you have on the server. But it's important to recognize that we are making the front ends complex for a very good reason. They're also getting more responsive, more resilient, and more efficient. This is a spectrum, and your app ideally touches multiple parts of this spectrum depending on the use case. So let's quickly recap. Events are a really powerful tool, and we haven't yet fully explored the power of event-driven architecture when it comes to building full-stack apps. There's some really nice benefits we get by pushing events and business logic all the way to the clients and allowing them to build local views of that events or do optimistic updates on top of it. This is amazing for interaction-heavy use cases like dashboards, internal tools, productivity apps, and like any architecture, it should be handled with care. Thank you very much. That's the end of my talk. If you like that talk, once again, go and please make sure you check out my YouTube content and connect with me on Blue Sky so that we can continue talking about this.